So finding the inverse of a matrix, let's start off with a definition. So have an n by n matrix A is called non-singular or invertible if there exists, and remember this reverse E, it means there exists, an n by n matrix B such that A times B equals B times A equals the n by n identity matrix, which remember the identity matrix is that n by n matrix where everything on the main diagonal is a 1. So the analogy as far as real numbers is concerned is kind of like taking the number 2 and multiplying it by 1/2, you get 1, or 1/2 times 2, you get 1 because the 2's cancel. Well, 2 and 1/2 are in some sense inverses of each other, so when you multiply them you get the identity for the numbers, the real numbers, which is 1. Well, the analogous identity for matrices is the 1 and along the main diagonal. So this is the definition. An n by n matrix A is called non-singular or invertible if there exists an n by n matrix B such that this holds. A times B equals B times A gives you the identity matrix. Okay, so B is called the inverse. A. Oh, real quickly, both of these terms are used interchangeably. Sometimes I'm going to use non-singular, sometimes I'm going to use invertible. To be perfectly honest with you, to this day, for me, non-singular, it always takes me a couple of seconds to remember what that actually means. So when we say non-singular, we mean that it's invertible. That means an inverse actually exists. We're going to run across in a minute matrices that are singular, which means that they're non-invertible, which means that an inverse doesn't exist. So again, you're welcome to use each one. We'll be using both interchangeably, and eventually I think you'll just be comfortable with either one. Okay. And as we just said, if no such matrix exists, then A is singular or non-invertible. I think some of the confusion comes from the fact that sometimes we use non-singular and invertible and singular non-invertible. Okay, so let's just take an example. A nice little 2 by 2. We have 2, 3, 2, 2. This matrix right here. And again, use mathematical software. It gives you the inverse just like this. So B happens to be -1, 3/2, 1, -1. So there are two matrices, A and B. Well, when we actually multiply A times B, and when we multiply B times A, and remember, matrix multiplication does not commute, so they're not necessarily equal, but in this case, AB does equal BA, and they both happen to equal the identity matrix, which is equivalent to this thing, 0, 1. Again, a matrix with 1s along the main diagonal. Okay. If a matrix has an inverse, the inverse is unique. Again, you can't have 2 or 3 or 4 different inverses. You only have one. We won't prove this, but it is a very, actually it's a rather quick proof, but we won't worry about that. We're concerned with using this idea as opposed to proving it. Okay, let's talk a little bit about notation. We want to denote the inverse of A as A with a little -1 as a superscript. And B, which means nota bene, which means, notice this very carefully. This is symbolic, okay? What that means, this a to the -1, it's a symbol. This a to the -1 does not mean 1 over a. This doesn't work for matrices. It's not defined. This is strictly a symbol that we use. Sure, you're used to seeing numbers like 2 to the -1, which is equivalent to 1/2. You just flip it. That's not the same here. We use the same symbolism, but it is only symbolic. It doesn't mean take 1 and divide by a matrix. Division by a matrix is not defined. It's not even something that we can deal with. But so bear that in mind. Excuse me. Now let's list a couple of the properties of non-singular matrices. And again, non-singular means invertible, ones that actually have an inverse. And recall again, we're talking about square matrices, n by n, 2 by 2, 3 by 3, 4 by 4, and so on. We don't speak of inverses of other matrices. Okay, property A. If I have the inverse, and if I take the inverse of the inverse, I recover A, which makes sense. You take the inverse again, you're back where you started, which is actually the definition of inverse. It works in a circle. If you remember dealing with inverse functions, it works the same way. B, if I take two matrices, A and B, and multiply them, and then take the inverse, I can actually get the same thing if I take the inverse of B first, multiply by the inverse of A. And notice the order here. This is very, very important. Just like with a transpose. When we did A times B transpose, that's equal to B transpose times A transpose. This same thing here. Those of you that are actually working from a book are interested in actually seeing the proof of this, I would encourage you to take a look at it. Again, the proof is not complicated, it's just a little tedious in the sense that you're dealing with every individual little detail. So it's easy to follow, it's just arithmetic. But it's sort of interesting to see how something which is not very intuitive would actually end up looking like this. So make sure that the order is correct. We also have a B prime, which is just the same thing for multiple entries. So if I have, for example, A times B times C times D, so on, inverse, well, I just reverse them. I'll just do it backwards. That's equal to D inverse times C inverse, B inverse, A inverse. Just work your way backwards, just like the transpose. And C, our final property, if we take a matrix and take the transpose of it, and then take the inverse of it, well, what we can do is just take the inverse first, and then take the transpose. In other words, the transpose and the inverse are switchable. Okay. Let's see what we